Hello. So, this is the next lecture, which is a continuation of modal analysis of continuous system. In the last lecture, we have talked how to find the equation of motion after modal analysis, how to perform modal analysis, and how to solve. We have solved an example of free vibration using modal analysis. In this lecture, we will solve two problems on force vibration using modal analysis. So, let us go back to the problem that we are going to solve. So, we have this simply supported beam again. So, we have a simply supported beam which has a uniform cross section. Let us say that the flexural rigidity is E I, where E is the Young's modulus, I is the second moment of inertia, and E I is uniform throughout the beam, as well as M is the mass distribution, which is also uniform, and we are denoting as M. Now, a load of P sin omega t is acting at the midpoint of the beam. So, P sin omega t is acting at the midpoint of the beam at L by 2. So, L is the total length of the beam. Now, the problem is that we need to find out the response y x t because of this load applied to the beam. So, let us see how are we going to find out the response of the system. So, let me write down the equation of motion first. So, the equation of motion is given as now let us see what is this f x t. So, f x t is the external load applied to the beam. We all know that. Now, how am I mathematically going to express the f x t that is acting on the beam? So, f x t is a point load. So, it is acting at a single point on the beam. The time variation of the load is sinusoidal, which is given as sin omega t, where omega is the driving frequency or the frequency of the applied load. So, how am I going to express this force mathematically? So, if you go back to some of the earlier lectures, we have seen any such point phenomena or any such single point phenomena can be expressed well by using Dirac delta function. So, this force can also be expressed using Dirac delta function. So, this force I can actually write as P into del x minus L by 2 into sin omega t. So, this del x, this is my Dirac delta function. This del x minus L by 2 is denoting that this entire force is acting only at x equal to L by 2, because this Dirac delta function by definition is 0 everywhere except at x equals to L by 2. So, this therefore is a correct expression for the midpoint sinusoidal load being applied to the simply supported beam. So, now we see that this expression for the force has a x part, has a spatial dimension part, has a time part which is given by sin omega t. Now, let us see how to solve the problem. So, before solving the problem, we know the natural frequency of a simply supported beam. Let me just write it down. I should again say that we can always find, we know how to find out the natural frequency, but here to save time, but here to save time I am right away giving the expression. Similarly, the mass normalized mode shape is given as where R so all this are done. So, now let us move into finding out the solution of this equation. So, after modal analysis, we can write the equation of motion as omega r square right. So, what I have done is this is nothing but 0 to L phi r x into f x comma t dx. So, this whole expression is just the expanded form of this, which is equal to q r t, right. So, now if I so, let me see what is going to happen to this. So, I am integrating it over dx. So, I can actually take out p root over 2 by m l sin omega t. And if we go back to our lecture where we discussed a bit about Dirac delta function, we have seen that can actually be written as so we have talked about this when we were dealing with impulse response. We have seen that integration of any function over the domain of the function with respect to the Dirac delta function is always equal to the value of the function at the non-zero point of the Dirac delta function. So, this is the expression that we got for Dirac delta function. Therefore, I can this whole right hand side is going to be So, this is going to be my right hand side, which is a function of time or the QRT. So, now my equation of motion after modal analysis is complete. It is looking exactly like the equation of single degree of freedom system for a sinusoidal force. So, this can be further simplified and written as A0 into sin omega t, where A0 is going to be P root over 2 pi ml sin pi r by 2. So, the value of sin pi r by 2 is going to be either 1, 0 or minus 1 depending on the value of r. We will deal with that later. So, A0 is this. So, this expression therefore is the is nothing but the equation of motion of a single degree of freedom system with a sinusoidal load or harmonic load, and we know very well how to solve this equation and get the value of eta r. So, let us try to do that. If we do that, we will see that eta r t is going to end up as A0 by omega r square minus omega square into sin omega t, where omega is the forcing frequency or is the forcing frequency or driving frequency, and omega r is the rth natural frequency. And of course, we have found out A earlier, A0 earlier, which was nothing but P into root over 2 pi ml sin pi r by 2. So, this is going to be the expression for eta r. So, once we know eta r, we can very easily find out y x t, which is summation of so, this is therefore the solution of y x t. So, we know all the terms on the right hand side, and therefore, we know the expression for x y of x comma t, which is the physical response of the Euler-Bernoulli beam because of the pointed sinusoidal load acting at the midspan of the beam. So, with this, let us move into the next problem, which is the problem of a moving load. So, this problem is simply an extension of the previous problem that we did, where we had this simply supported beam with uniform cross section. So, of length L, so let this be x equal to 0, let this be x equal to L. It has an uniform cross section and EI is the flexural rigidity and M is the distributed uniform distributed mass. Now, what we have here is a point load P at any arbitrary distance x, and this P is moving with a horizontal velocity of v. This problem is a simplification of the problem of a traffic movement over a bridge. A bridge can be very accurately modeled as a simply supported beam. The span of a bridge can be very accurately modeled as a simply supported beam. So, to find the response of the bridge due to traffic movement, we can always simplify the problem as a moving load over a simply supported beam. So, this P load is nothing but the load imparted by a vehicle which is moving with a speed or velocity of v, and the load of the vehicle is modeled as P, and at t equals to 0, the load was at x equal to 0. So, let me try to explain the problem in another word. So, we have a simply supported beam of length L and flexural rigidity EI and uniform mass distribution M. The beam has an uniform cross section. Now, there is a moving load which is mimicking a car or a vehicle or a traffic that is moving on the bridge. So, at t equals to 0, this point load P was at x equal to 0, and then onward it started moving along the length of the beam with a velocity, uniform velocity or speed v. How are we going to find out the response of the beam because of this kind of moving load, or the response of beam under this condition? This problem is a very simplified problem of analyzing the vibration of a bridge undergoing movement of traffic or movement of vehicles and cars. So, let us now see how are we going to solve the problem. So, let me first write down the equation of motion. If we write down the equation of motion, the equation of motion is going to be EI how do I write the force now? So, that is going to be right hand side is a force because an externally applied force is acting. How am I going to write the force? So, let us see, the magnitude of the force is P. Now, the location of force is any x. Now, what is that x? That x is Vt. So, this x is going to be Vt, because at t equals to 0, it was at x equal to 0. So, by time t, it has moved a distance of Vt. So, at any time instance t, this concentrated load is at a distance of x equal to Vt. So, therefore, at any time instance t, this load is a point load acting at a point of x equal to Vt. So, how am I going to mathematically represent that? I can mathematically represent that by a Dirac delta function of x minus v t. This is going to give me the expression of the force, right. So, now once we get the expression of the force, then solving the problem is pretty straightforward. So, how are we going to solve the problem? So, let us see how we are going to solve the problem. So, let me do modal analysis, and after modal analysis, we have the equation of motion as eta r double dot omega r square into eta is going to be 0 to L phi r x f x comma t dx, which is going to be that can be written as P into root over 2 by ml So, now referring back to the previous problem, we can say that this whole integral is going to get simplified to p by root over m l into sine of pi r v t by l. So, the driving frequency therefore, so let me before getting into this. So, we can say that my equation of motion is eta r double dot plus omega r square into eta r is equal to this. So, this can further be written as some constant a 0 into sine pi r v by L into t, where a 0 is p into root over 2 by m L. Now, if we look into this problem, this also eventually boils down to the problem of harmonic loading. So, the right hand side is nothing but a sinusoidal or harmonic loading with a frequency of pi r v by L. And we can solve this problem exactly in the same way as we solved the previous problem using harmonic analysis, and eta r t is going to be a 0 by omega r square minus omega square into sine pi r v by L into t, where omega is pi r v by L, which is the driving frequency or the excitation forcing frequency. So, this again y x comma t can actually be written as a 0 can be written as summation of r 1 to n infinity into root over 2 by m L into a 0 by omega r square. So, this is the solution of the system. This is the solution of the system or the response of the system to the moving load. Now, you can see that why harmonic analysis is so important, because we can see even the traffic movement can actually be modeled as a harmonic load problem, and since we know all the details of harmonic analysis, we can very well physically analyze this response. One example is that the driving frequency, which depends on the velocity of the moving vehicle, should never be equal to any of the natural frequencies of the bridge. If so happens, there will be a resonance condition, and we have to take care to solve the problem in such a way that the natural frequencies of the bridge is never equal to the driving frequency that is coming because of the moving load. So, several such analysis can be done by looking in detail into the solution, and but what we have done today is that we have understood how formally, using modal analysis technique, we can solve free and force vibration problem of any continuous system, and the solution using modal analysis eventually boils down to the solution of a single degree of freedom like equation, which we know in detail how to solve. So, with this we will end today's lecture. In next lecture onwards, we will talk about approximate method, where we will try to solve the vibration problem of bars and beam with non-uniform cross section. So, all these days we have dealt with beams and bar which had uniform cross section or uniform mass distribution, but in the next two lecture we will talk about approximate method by which we can analyze beams and bar having a non-uniform cross section. So, till then, thanks a lot.